Welcome. I hope people online can hear me. Okay, I'll just keep it in my hand. So this is the second session of the day, which is devoted to power systems, general energy system stability, and all the interesting phenomena. So first of all, I have to introduce myself. So my name is Janusz Bialek, and I'm professor of power and energy systems from Newcastle University. And the main speaker today will be Shurooque Baloch from Electricity System Operator, which kindly has agreed to give a talk about those interesting things. So Shurooque will give the main presentation. So let me just say a few words of introduction. I hope I'm not stealing your slides. So basically, the reason we are talking about stability now, stability, of course, is well-known subject, well-threaded subject, and we thought we know everything about power system stability. But we have a changing world, obviously. So it's the most profound change in power systems since the war of currents, DC versus AC, has been won by AC at the end of 19th century. DC world is actually coming back with vengeance, as we'll talk a little bit about today. But basically, what happened was that the old world of traditional, relatively few big power stations with their synchronous machines provided electricity for the system, and that the combined inertia provided energy buffer for the system to ride through any contingencies. Now those big synchronous generators are being increasingly replaced by wind, solar batteries, which are connected to the grid asynchronously by means of inverters. Inverters are basically means they change electricity from DC to AC. And altogether they are known under the name of inverter-based resources, IBR. And they completely change the characteristics of the system. So we are in the new unknown world, and that's why we need to analyze it, and we need help of mathematicians, because the whole theme of the workshop is, of course, a math behind energy systems. The main thing which probably everyone realizes about is the diminishing inertia. The inertia in power systems in this country and other countries in the world is going down quite dramatically, and that has profound consequences for frequency control and essentially for keeping people the system stable. And this is something which is one main theme, but there are many aspects of system services which those synchronous generators provided, and those new inverters may provide if they are programmed appropriately, or may not provide, just depending of how you do it, because those inverters are highly programmable. It's a big degree of freedom, which of course is a big opportunity, but at the same time is a big risk, as we'll see later. So when talking about the stability, well, in power systems, we have many different aspects of stability. Main thing used to be electromechanical stability, which means all those rotating masses, how they interact with each other, oscillations, frequency oscillations, and voltage stability. And we have well-established tools to analyze stability, like, for example, eigenvalue analysis. But in the new world, rather than having those relatively few in the range of 100 of synchronous generators, we have thousands, or possibly in the future hundreds of thousands of devices, each with its own controller provided by those inverters, and there are many possible interactions which may threaten system stability. Because all those inverters, they have their own control, quite complicated control systems with many variables, with many gains, and they may create interactions, unstable interactions, threatening stability. And indeed, there is an example, and I asked Shurooque to talk a little bit about it, of 8 Hz oscillations in the north of Scotland when there was no synchronous generation, which ESO is still struggling to understand and to explain. And now one reason they have a problem to do it is that we don't have models of those inverters, because quite often there are proprietary models provided by vendors who do not want to disclose the exact model of their controllers. They just give some information like compiled simulation or so-called impedance sweep, but you don't have exact models, but you know how those how those inverters are built. So what we need, and this is why we are here, well, that's why I'm here, we need help of mathematicians to help us to analyze and understand stability of this new power system. And this is made, as I said, difficult because we don't have those models. So there's a question of identification of the models and then analyzing stability. And stability is one of those very mathematical areas of engineering which heavy math, new math is needed. And that's why I'm here. And I hope to learn something about it. Well, the subject area is quite interdisciplinary because it has also implications for economics, and that's why I'm very pleased to see David over here. Because as we replace synchronous generators, there are many services which used to be provided free by synchronous generators, like inertia and others, but now you have to pay for them. So it's the question of how to set up markets, how to set up all those ancillary services. We've just had a quick chat with David before, and there are now too many of those services. And if the question is that they will support each other, they don't pull in different directions. So this is all I want to just to say as a short introduction. So now I give floor to Shurooque, who is an expert on the subject, and I'm sure she will tell us many interesting things. Thank you.
Hi everyone. Not won't call myself an expert, but yeah, hopefully I'll be able to answer most of the questions you'll have today. And I'm told I'm the only speaker, so I'll probably go through the slides, but I'm happy to have more conversation and discussion as well at the end as well. So yeah, I'm Shurooque. That's my background is power system engineer since last 12 years now, and we're working with DSO, joined National Grid, went with National Grid, and DSO separated 4 years ago. So now we work and the National Grid DSO, a separate company. And if you weren't aware, we are becoming a future system operator. We will be called something else, of course, not future system operator, but we are becoming an independent system operator soon. So our roles and responsibilities will look very different going forward for the GB network. Okay, so in case people didn't know what the role of DSO is, just a very quick overview. So that's the GB network, and we have three onshore transmission system owners. One is National Grid for England and Wales, and we have two Scottish transmission owners in Scotland. And of course, this is just the onshore network. We also have now what we call OFTOs, the offshore transmission owners as well. And the offshore transmission owner assets are essentially the cables, the long HVDC links that connect the offshore wind farms with the onshore network. But they are regulated entities, and they are classified as transmission owners as well. Yeah, just general role of ESO. We do not own any assets. We just operate the network. And oh, somebody's not seeing the full screen. I think somebody left a message. They're not seeing the full screen. Should I attempt to reshare? I can try. So share.
It's not your problem, it's the remote. Ah, that's it. No, now you're just seeing my name. I don't want that. That's it.
Is that working?
Yes.
Perfect. Okay. So the National Grid system operator, we don't own any equipment on the network. All we do is operate the network, and but we allow or define how parties connect to the system. So system operator will be the ones who issues connection offers, and we work with the TOs to be able to give offer dates and connection works that are required for somebody to connect. We also play a very big part in deciding or recommending what investments on the transmission system should be happening. So the TOs are the one who build the assets, but ESO is the one who probably carries out a lot of cost-benefit analysis for something to be built. Yeah, and of course we are responsible for all the charging and billing in the context of GB consumers at the end of the day. So that's the general role of the system operator. And I guess the biggest role is we maintain supply and demand in a real time, 24/7. That's the second by second. That's the main role of the system operator. The rest of the stuff is all long term and a business as usual activity. So, what's changing? I guess most of you are already aware of all of this. I don't have to say there are government targets and different things regarding renewable generation, how to get to net zero or increasing our share of renewables in the system. And the biggest driver was 2 years ago, the decommissioning of all the coal plants by 2024. So we see the energy landscape changing. We have seen a lot of wind connecting in the last decade. And due to the government targets, we would expect a lot more renewables will be appearing on the system coming in coming years. The system is changing from where we were 10, 20 years ago, 30 years ago. We are in a completely different scenario, and we will be in a completely different scenario in 5 to 10 years' time as well. So you can see there is, we expect at least around 50 gigawatts of offshore wind by 2030. 50 gigawatts is a big number. Our peak demand is around 50 to 55. So thinking of that number, it feels like there's a lot of wind that's still to be connecting on the system. And we also expect a lot of new technologies such as hydrogen as well coming on. There's a lot of talk about it. We will have to see when these projects develop and if they come on the system and what role they play in terms of electric system. We would see hydrogen perhaps playing a big part in storage on the storage side, perhaps similar to batteries. And 2025, which is not far, ESO has an ambition to operate the system carbon-free. What that means is that if the market gave us a dispatch of generators that are carbon-free, we wouldn't want to run any carbon plant in certain hours of the year. That is the idea. It doesn't mean that we will be able to operate a network 24 hours a day or 365 days in a year carbon-free, because we are not there yet in terms of the generation content we have. Okay. So, yeah. So, what's the challenge with zero carbon operation? When I say zero carbon operation, essentially, we're talking about wind being a key generator or generation source, and then the nuclear is our main generation source as well. We do have a lot of hydro in our network. We have pump storage as well in the network. They're all synchronous plants, the three of them. So, but the gas and the coal are the ones that are declining, and coal is going to be decommissioned in the next year. So we want to be able to operate the network that we were able to operate reliably and safely when we had the gas and coal generators in the future as well, but without them. So in order to do that, our challenges are becoming different. So we'll have challenges to maintain frequency, which is a traditional response provided by governors of the synchronous generators, which are no longer there anymore in the future. Inertia, again, as mentioned again before, inertia is something that's property of a rotating machine that's synchronized to the system, and that rotating machine is essentially a rotating mass, like a coal, gas, or any big synchronous plant. These plants are not there anymore, so we don't have inertia perhaps in the future years from these sources of generation. And in order to operate the system without these gas and coal plants in the future, we need to do something different. So we'll have to do something different in terms of either services or building of assets, or how we, what sort of services we see on the system. Perfect.
John McDee from Penn State again. So I'm just curious what type of models or assets thinking there is around dealing with the peak demands, which typically are what the natural gas seems to be extremely effective for.
Maybe that's for discussion. Yes. Okay.
I'm happy to answer. Yeah, no, that's absolutely fine. I think you're talking about how do we, at the moment, historically, we have thought about peak systems and investment in the peak system because our issues have been transferring bulk power from one area to another, and that's a consideration we have considered for investment in the network. Going forward, we are going in a world where this is probabilistic comes in, a lot of probabilistic modeling, understanding how we interpret future scenarios, and not just the peak analysis, but we also need to look at minimum demand periods and other scenarios in the year that could help us decide what investment decisions we make. Probably come back to you afterwards as well. Yeah, that's fine. Yeah. So just to say, I mean, we say we want to operate a zero carbon system. We are not really far off that in the GB. We have on the 23rd of May 2020, we had 85% of energy coming from zero carbon generation or non-fossil fuel generation. And we had 66% of wind share on the last year's January. So we are seeing periods in a year where we are getting a lot of wind and renewable generation on the system. And as system operator, we may not be there to be able to allow that all generations to be available, to be operating on the network in a given time. We have to take some actions because we can't operate with that level of generation perhaps at all times. So some of the key engineering challenges with, I'll just briefly go through them. And so just to say, if we have lots of renewable generation, which is connecting through the converters or the power electronics, and they're not synchronized with the system the way synchronous generators are, we are seeing different challenges in terms of system parameters. So our frequency becomes difficult to control. Stability, which is inertia, and levels of short circuit level, which we call in the system, they're declining. Voltage, which is something traditionally we get support, dynamic voltage support we get from traditional synchronous generators. Going forward, we are getting them from converters, but perhaps the behavior of the response is different. And the way the network was built, if you think of the GB network, we had historic coal power stations in the middle of the country. Those plants have decommissioned, they have disappeared. We have wind appearing on the peripheries of the network or somewhere around where there is a lot of wind, like Scotland. The generation mix has changed, the location of generation has changed, the demand hasn't changed. The demand is still south of the country. We don't have that much demand in Scotland, where we have a lot of wind generation, for example. So the flows on the network, the way the electricity behavior is changing, it's because of the patterns of the generation, where generation is appearing. So where we had generation before, it could provide us local voltage support. It's not there anymore. And there's nothing to replace it, for example, in middle of the country, where we had like large coal power stations. So we have to do something different in those regions, perhaps, because we're losing something from there. So there are a lot of considerations how different parameters in the network can get affected by how and where the generation is appearing and what sort of generation demand disperse is happening in the few years. And of course, thermal being a big consideration, which everybody probably relates more to, because there's a lot of wind in a particular region where demand is less, for example, Scotland. There's always consideration of how much can we allow for power flow from one region to another, with and without the investment of the network. Easy answer in terms of easy answer is to build lines, but is that the economic thing to do in the system, or there is more wider consideration on how we operate the network in terms of constraints and reducing generation in a particular region? So all of these things interact with each other. There's no simple answer, and all of the parameters have a link with each other as well. The biggest issue, perhaps in the future, could also be how we manage storage. And then the flexibility parameter, how the technologies behave or can be flexible or not flexible, will impact how we operate the network as well. As you may know, the old nuclear power stations, they're typically very inflexible. So if they are at a particular megawatt value at a particular time, it's not easy to reduce the output or increase the output for them. So there are considerations for the generation technologies as well to be flexible, because that would mean the system operator has more options to be able to ramp up or down the capacity of a generator. This is just to rephrase of what I've been saying. It's just we expect a lot of renewable generation coming onto the system the next few decades. The greens are where it's a lot, that's all wind, onshore and offshore, and we just see it growing over the coming years. This graph, just to give a bit of context of what I mean by system operator taking action. So there are two lines on this graph. One is red and one is blue. The blue line is what the market gives us as a dispatch in any given half an hour, which is a typical settlement period for our control room. And what that means is that if that blue line is not something that the system can accommodate, for example, in terms of the capacity of the network, it could have thermal issues, it could have voltage issues or stability issues, we as system operator have to take actions, which we call constraint actions, with a pay generator to turn off or on. And those actions have consequences in terms of cost for us. And so you could see the blue line changes to the red line, which is where we have taken actions as system operator, which have cost associated with them, and we reduce the amount of different generation in different regions. So in theory, market dispatch will give us a very green renewable dispatch, but we can't operate that level of renewable in a given half an hour. So we will have to do something to reduce that output. And we probably will be synchronizing some synchronous plants like gas, for example, if there was a voltage issue in a region or we had an inertia issue on a national level. So there are different actions we would consider, and that's where we result with the what we will get in real-time dispatch. So the real-time dispatch is essentially the red line.
Why are the blue lines at the low penetration, like 40%?
So the blue lines are what the market gives us. So if it's a windy day, the market will give us high volumes of wind.
Low level of penetration, 40%. I understand why they are at the top, but why at the bottom?
Oh, if it's a scenario where wind is less, it's not windy, for example, the demand is low, for example. So these are different times of the year. So the demand varies as well in the system. The generation patterns vary in the system as well. But it's the key thing is the difference between the red line and the blue line. The red line itself will be based on weather pattern or whatever is happening in real time in terms of the other fuel sources and other things as well. Okay. So inertia. So maybe you have seen these graphs before if you've been to any of the National Grid ESO publications or presentations. So just to give a feel of where we were. So the graph on the bottom left is where you could see different historic years of the levels of inertia we saw in the network in a given year. So this is just a annual distribution to say what was the level of inertia within the year and how much amount of time. So we can consistently see the fainter lines to the darker lines are where we're going. The most historic year to the most recent year, we can see that the inertia is just coming down in all those years. And similarly for considering ESO's future energy scenarios, which are just some outlooks of how future may look like, we see inertia declining over the next few years. Just to explain how to read this graph in case somebody's confused, because it's really difficult to follow sometimes. So the orange line is the 2021 level of inertia. The other two lines are blue line is 2026 and the green line is 2031. And all it's trying to say is that 20% of the year, for example, if you look at point 2, 20% of the year, the inertia was below 100 GVA seconds or 100 gigawatt seconds. So all we are seeing is that across all these scenarios, we are spending more time towards the lower end of inertia, most proportion of the year at lower levels of inertia rather than the higher end of inertia. And this just means that in the past, we may have thought that if we look at these graphs for 2008 to 2019, we see that maybe we're spending less than 20% of the time at less than 200 GB a second, which is still quite a high number compared to the future years.
Minimal inertia requirement due to rock-off requirement?
Which one?
Well, national minimum inertia requirement, but on
Yeah. So sorry, yeah, I should explain. So this line, the dotted line, is 120 GVA seconds at the moment. And this 120 GVA seconds comes from the rate of change of frequency, which is 1 hertz per second. At the moment, our system's largest loss is, I think, less than 1800. But in the future, our largest loss in the system will be 1800 megawatts. So this line will change in the future based on the rock-off value and the largest loss in the system. But at the moment, that's what the current system planning limits are. We review the rock-off, we review the inertia limits every year as a consequence of August the 9th event that happened 2 years ago or 3 years ago when we had a issue with London. And as a result of that, there's an annual review of the our supply and security and quality of supply standards every year. So every year for next 12 months, we review what inertia limits we would apply and what sort of reserve we would buy in order to plan that. So yes, so that's the current 120 GVA seconds, but in next 12 months, it could be different. And going forward, if you have seen our recent operability strategy report, we are our inertia limits would be 106 GVA seconds, considering the 1 hertz per second and 1800 megawatt loss. So we have to be able to operate the network with that much level of inertia. Okay.
Is there a simple relationship?
David Newbury, is there a simple relationship between inertia and the megawatts attached to the spinning turbines? And if so, what is it?
So, normally, the inertia equation side, they would just be considering the speed at which the machine runs, which would dictate how much kinetic energy. So it's a relationship between the kinetic energy in the machine and what it outputs as the mechanical energy. So essentially, there's a relationship. Maybe it's not exact megawatt to megawatt, but it's the capacity of the machine and the energy it stores.
They're all going at the same speed.
They are all going at the same speed, yes. So the bigger the mass is, essentially it's a mass issue. The bigger the mass is, the more rotating energy will be, and it'll provide more inertia. So that's how we interpret inertia for our traditional rotating machine. The concept of inertia is also exists for the new technologies such as grid forming converters, not the grid following converters, just to distinguish between the two. And they are not rotating masses anymore, but it's the control system that's dictating what we call inertia, which is where the issues are becoming challenging and interesting as well at the same time. Yeah. Okay. So the first thing we are, of course, losing because of the synchronous generators declining system is inertia. But the second thing, or major thing, is the short circuit levels. In the past, if you don't know what short circuit levels are, a quick explanation. So short circuit level is a measure of how much fault current, or if something faulted on the network, how much current can flow through that fault. So very basic explanation. And the way, why we worry about it or why we think it's important is because the fault current dictates different things in the network. So the protection systems, the key protection systems, how protection systems isolate faults in the network, because the faults have to be isolated, otherwise they could keep tripping other things on the network, or the equipment could be damaged. The protection system that determine how they should operate rely on the fault current. So if there wasn't sufficient fault current, the protection systems will not detect the fault, and hence they may not operate, and which could have a broader consequence to the integrity of the system. So we need protection systems to work. That's one aspect. But the converters, the renewable generation that's connecting to these power electronics, they seem to be relying on some control systems which don't seem to work at low fault currents. So there's an issue with the technology that they need a level of system fault current in order to be able to operate, or operate correctly is the word rather than be able to operate. So there are different parameters, different considerations of why fault currents are important in the network. And if there are technologies like synchronous generators, which inherently or instantaneously respond to system changes. If the voltage goes down or frequency goes down, they inject the right level of current or absorb the right level of current. If we have those technologies, the system recovers faster if something went wrong. But technologies like converters that rely on the measurements or control algorithms, there is delay in them, and then they don't respond as quickly as a synchronous generator would. Hence, the system does not recover fast enough. And if the system does not recover fast enough and we don't understand if the converter is supposed to do what's supposed to do with the fault levels it's seeing, then there's a problem. So there's a wider issue around how the converters behave with low short circuit level in the network. So that's the key. This is a very simple explanation. Hopefully it makes sense. But just to give a flavor, it's just saying that, yeah, different areas of the country, we expect fault levels to decline in the future years. But that's just a consequence because of synchronous generators not being on the network, because synchronous generators provide us the most voltage feed in the network. Okay, hopefully I haven't lost anyone on any of these slides. I'll move on. Sorry, I have to pass this.
Tony Rolls, an engineer of thought. It's not my specialist area, so I ask a naive question. People have said that you talked about inverters, that they provide some synthetic inertia. You talked about the previous slide. I think you're not showing any synthetic inertia there because you're just counting rotating machines. What's your view about synthetic inertia?
So yeah, the previous slides I've shown are just based on the rotating plans contributing to inertia, because we do not yet have any converters that provide this inertia in the network. So there are two types of converter technologies broadly categorized. One is the grid forming converters and one is grid following converters. The grid following converters are the traditional converters where all the renewable generation is currently connected, the HVDC interconnectors, everything uses that technology. That's widely accepted technology, and that's what's built. I guess it's cheaper to build because it's established, so hence everybody will opt for it. The new form of converter technology, which is grid following technology, is where the concept of inertia comes in. And it's the algorithms or the control logics they use is trying to mimic a synchronous generator essentially. And it creates its own voltage waveform, and it tries to resist any change in the network voltage or frequency. So that's what distinguishes the two technologies. So far in the GB network, we don't yet have any grid forming converters, and if we in the future we are expecting them because we have signed some contracts with for ancillary services with a few of them. But those technologies are able to provide inertia. Once they commission, we will actually have proof, more proof of them at large scale how they contribute or not to the system. But of course, there are lots of innovation projects that have proved the concept for inertia for grid forming technology. So wind farm in Scotland, if you haven't heard, it's the Shurooque one with SSA Renewables, or sorry, SPR, Scottish Power Renewables. They tested grid forming capability on the wind farm at their site. So there are, and across the world, there are different manufacturers perhaps that test the capability, perhaps, but it's not deployed at large scale is where we are. But in the future, the picture could change. At the moment, according to our grid code, the GB grid code, we do not have an obligatory grid forming obligation on any new connections. Perhaps if we have that in the future, our calculations will account for it, because we expect anybody who can act with a converter will have that capability. So yeah, it's there. So just a brief flavor about some inertia spend in the last few years. So why we worry about inertia is because inertia, essentially, there's a relationship between inertia and the frequency. If you don't have enough inertia in the system, frequency, the rate at which the frequency falls, the rock off, the rate of change of frequency, it's really fast. If the frequency falls really, really fast, our frequency response services don't kick in, then things will start tripping. That's the simple answer, a simple way to explain it. So the rate of change of frequency has to be kept above a certain level so that things don't start tripping. And that's where inertia comes in, because inertia means that more rotating plant or more energy can be injected in the network, and it's this imbalance that's maintained on the network. So in the past few years, you could see the cost, the amount of money we are spending to increase inertia on the network. So this is the difference between the red line and the blue line in the previous slides. The actions we have to take in order to maintain inertia to a level so that we get to a place where we feel comfortable that nothing will trip or nothing bad will happen according to our license obligations. So there is a significant spend across different years.
Why is it dropping last year?
Probably, I'm just taking a wild guess here. I have no idea, but the guess would be because we have some stability contracts for inertia. So those contracts start becoming live in 2022. So that would be, my guess would be that would be the reason that we are not spending more in real time, because we have long-term contracts with some plants to be able to provide this inertia and across different time frames. That is my guess, but I would have to exactly find out the reason. But yeah.
If for inertia you haven't got any grid forming inverters, this is all spinning reserve. So this is coal-fired and gas-fired stations running without delivering power on the basis that their inertia might be used. So it's nothing to do with battery services or anything like that.
Yeah. So the contracts that I'm mentioning are synchronous compensator or condenser contracts with flywheels. So they're not gas or coal plants we are talking about here. The contracts we have for stability, Pathfinder, which if you haven't heard, we signed contracts with a number of units, I think 8 or 9 units, and they are synchronous compensators. So they would spin at 0 megawatts. They're just using demand electricity as a demand energy, and they just rotate it. So some of them have flywheels, some of them don't have flywheels. The flywheel is just added to increase the mass, to increase the inertia. So there's some technologies out there that can do it without that. So the contracts are with them, not with the coal or gas power plants. And I think just to mention, we are also looking at some other response services that we get fast frequency response in network, and it's just how we procure different services for different reasons. We just have to change the way we do things. The same things we did in the past but don't work. That's the key message here. So just to re-mention the same thing, a lot of inertia comes from the rotating plant. There is some load contribution for inertia. The question is, what is it? As system operator, we only have visibility of what connects to the transmission network. So we do not know all the time what's happening below that, so the distribution network. So there's a big issue with how much information we get as system operator, and perhaps in the future where the distribution system operators become more active, or they have more defined roles. There could be different responsibilities and how things flow between the ESO and the DSOs. But at the moment where we balance the system at the transmission level. We do not know what goes on in the distribution network. We get data. We have data exchange mechanisms with the distribution network operators as part of the regular data exchange platforms, but we don't have real-time data. It's just the planning data that we exchange with them. So in terms of our inertia calculations, going back to the previous numbers in the graphs and stuff, we do consider a load contribution for inertia because we know that demand gives us some inertia because there are some motor loads or something else in the network. But what we don't know for sure is what that contribution is. At the moment, we make estimates on the percentage of demand that could be contributing in real time to inertia. Going forward, we'll have to do something different because that estimate may not be valid. And it goes back to the point about modeling of how do we know what that is in the future years as well. Inverter-based resources, at the moment, we don't have them, but in reality, going forward, there will be a lot of inverter-based resources would potentially provide this inertia. So I think in the past, it was easy for us to forecast inertia because it was all rotating plants. Majority bulk of inertia came from them, so it's a simple calculation for us. We could have done it. Going forward, we can't rely on it. The synchronous plants are just diminishing, and that's not what's left on the system anymore. So we have to do something different. So there are a few projects going on at the moment. If you haven't heard of them, it's real-time inertia monitoring projects where we have contracted two companies. One is GE and one is Reactive Technologies, which have got different methods of calculating or coming up with estimation of real-time inertia. So just a brief overview. I don't know a lot about them. There's a lot on our website if anyone's interested. The GE technology relies on PMUs, the phasor measurement units. So the idea is that phasor measurement units are deployed across different areas of the network, and in real time, they should be able to give us an indication of different measurements, and then the GE system applies some machine algorithm to predict what the inertia would look like ahead as well, and the real-time value as well. At the moment, these are being tested and trials. We have to wait for them to be validated. So that's why we have got two different approaches. And the second approach is the reactive technologies inertia measurement. So the way this works is slightly different. They've got different pulse injector modulators across the network. So what they do is just inject pulses across the network, and that's how they try to see how the system responds. And they just gather data or something, and then they come up with a value for inertia for different regions. Where we are with these things is we've deployed them. What we don't know is what we get in real time is right or wrong, and how do they match with each other or not, and how does it weigh against what we have been doing in the past. There's a huge difference, obviously, because the data we have used in the past is a single equation, for example, or a single estimate or an assumption. And obviously, this will give us more accurate information because inertia should be changing within an hour or a day based on demand generation and everything else in the network. So these are still being trialed, and there is a second step of the project, which is looking at validation. And then if these things are validated, then we'll hope that they should inform us how we should be looking at future planning as well. Yeah, actually, that was all inertia. Any questions? Oh, sorry.
Yes, hi, I'm Janusz. I'm with the Department of Engineering here at Cambridge. So my specialization is in control, but in recent years, I've been looking into these problems of grid forming control, how to make it scalable in larger networks. So I think I wanted to ask is whether you currently have any protocols for grid forming control, or you are looking to establish those in the future. And another kind of related question is whether this kind of protocol will need to be looked at in a different way relative to, let's say, existing grid code, because converters, they seem to have strong capping between their frequency and voltage control policies. They use frequency measurements to implement their voltage control. So whether kind of this kind of scheme needs to be looked at, let's say, from the perspective of the power electronics.
Yeah, so it's a very good question. So in terms of grid forming, in terms of the GB grid code, we have recently, I think sometime end of last year, we have recently introduced the minimum technical specification for grid forming technologies in the grid code. So now it is part of the grid code. However, just noting the GB grid code specification for the grid forming converters is not a mandatory specification. It is there. If somebody wanted to build a converter with the grid forming technology, they should be following that specification. That's the idea behind it. The reason the reason it's there is because there is still an opportunity for people to participate in a future stability market environment, because we are developing stability markets, and there will be an opportunity for people like with storage batteries to be able to trade inertia, perhaps in the short term or in those services. So the specification is there. There is still a talk from, there's recently been ideas from NSOE on grid forming technologies that they want to mandate it for any new converters connected system. So it could be something that GB as well as maybe thinks, we do think there is maybe merit in having that as a mandated obligation, but at the moment we are not there yet. In terms of the specific control frequency and control response algorithms, it's a difficult one. So we as system operator, we want to specify the performance characteristics of somebody connecting the network. we don't want to dictate how the control should be modeled because that becomes too complicated. And we don't want to limit the technologies when we get something. So we just want to define performance-based specifications so people should be able to meet the performance criteria as laid out in the grid code rather than the other way around. Yeah, please.
What about impedance-based specification?
Yeah. So, at the moment, when you say impedance-based specifications, you mean more like a design for the grid forming? Yeah. So the grid forming specification in the grid code at the moment is it talks about impedance a little bit, but it's based on virtual impedance, I believe, maybe as well. So you may want to look through that if you haven't, just to see if it's there or not. But we would. I mean, there is also for the grid forming converters, there is an there is a best practice working group with industry and academics. If you're interested to follow because I think that work group has just concluded. If you're interested to follow the conversation, just drop me a mail. I'm happy to link you with them. They probably know more than me on that.
So do these technologies also provide black start capability, and is that a looming problem?
Yeah, so they can in theory. So I think there are, so in terms of the synchronous generators, we normally consider them to be able to provide black start. In terms of conventional converters, there's an argument that they may need some backup supply in order to help with black start because they will have to have something to start them as well. But there are a few innovation projects that are exploring black start from HVDC connectors. I don't know what the outcome of that is, but we would expect the grid forming converters should be able to do a bit more than what the traditional converters do. But I think a lot of these things are probably innovation ideas at the moment. The services for black start are probably based on a combination of conventional plus storage or something along those lines.
You talked about grid code. Sorry, I missed the beginning. So if you've covered this, I apologize. Have you covered reliability of the system? My understanding is that the current system reliability is actually a customer disconnection likelihood, whereas in the future, where there's much more perturbations on the system, that unserved energy might be a better way of looking at it. You give the examples from the ESO's forward plan, and I think I looked through the whole of it. I didn't find the reliability, the changes in demand and the issues of reliability covered at all. Perhaps you could say something about that.
Yeah, that's fine. So at the moment, the reliability or the way we allow for redundancy or in the designing of operational timescales is covered by our security and quality of supply standard, SQSS. So SQSS will define how much we should be investing in that network. For example, if a demand was connecting to the network, it would define the values up to which we can lose the demand or beyond which we should be investing. So at the moment, that's covered in the context of SQSS. SQSS, again, is a industry document, and it is reviewed, and people across the industry can trigger change to it. So if there was something and then people triggered some change, then it could be that those standards are reviewed. There is a huge review of SQSS going on at the moment in some areas. I'm not sure if the reliability is one of the areas, but there are a few areas of SQSS that are currently being reviewed. Sorry. Yeah.
Thanks, Kristen. I think just following on from that, we're also dealing with quite different classes of event here. So in the storage work that you've been involved in that we'll hear about later, where my understanding is that's primarily concerned with supply-demand balance, effectively assuming, this is never really written down, but it's implicitly assuming that if there's a shortfall, then you can disconnect demand in a controlled manner. And there for that class of event, that's where we have the standard of 3 hours per year on average, and then I've been involved in the discussion as well over whether we should move to a different metric for that. But here we're dealing with dynamic stability related events, where I'm kind of heading towards saying, I don't want to say, I'm not quite sure what the right way to put it is. We intend that these will not happen. We intend that we will not have customer disconnection from these. But if you do get a serious disturbance related to dynamic stability, then there are measures in place to disconnect a limited number of customers to protect the integrity of the whole system. But actually estimating, actually quantifying risk of how often you would disconnect how many customers is extremely challenging there. So it tends, in practice, it tends to be dealt with by, it tends to be, in practice, we don't have the same sort of systematic ways of working through the link between the precise link between mitigation decisions and exactly what the risk is. But I think some of those points might be interesting topics for discussion through the fortnight, particularly some of these questions of decision analysis between operational policies and what that means in terms of risk of stability related events.
Okay, moving on to a slightly different topic related to stability. I've taken the slides that one of my colleagues presented 2 years ago when this actually happened. So they're still valid because a lot of things are still the same. I'm going to talk today. So we had some oscillations. I'll just go to the next slide. So we had some oscillations in Scotland last year, 2021. And what happened was we saw disturbances, oscillations between two areas of the network. So North Scotland, which was SSEN's area, and South Scotland, which is SPN, Scottish Power's area. And the disturbance actually lasted for quite a few seconds, you can see. And there are two oscillations, 30 minutes apart from the seen from the data. So the control room got worried, obviously, because the control room don't expect to see oscillations on the network. And of course, it's a panic mode for them if they see something like this. They in real time, people really worry about how they can secure the system. That's their priority. So for them, because they hadn't seen something like this before, they panicked, and obviously they were trying to put available generation, synchronized available generation in the region. So as a short-term mitigation, what they did was they synchronized additional hydros in Scotland, which were not running at that time. So when they did a few machines, synchronized a few machines, they saw the oscillations stamped out. So as an interim for a few days, that is what they applied as their operational strategy, because at this point, we don't know what the cause was of these events. And obviously, if these oscillations persisted, then some plant in the network could probably trip, and that would mean we lose generation, perhaps. And if we lose generation, it means that we probably lose another generator somewhere else. So it could obviously mean there could be a wider consequence in the network. So the priority for the control room is always to secure or get back to normal as soon as possible. So yeah, that was oscillation. So after of course, when the oscillation happened, at that time, they didn't know what was going on. Some small users tripped off in Scotland. It could be their protection settings, perhaps. So they did that. What we did was, obviously, as I said, so there's a lot. So of course, the event has happened. The general normal process would be once the event has happened, the ESO has to sort of come up with what we want to do next in terms of post-system analysis. So we have to work with the TOs, who are the owners of the areas of the network, and obviously with the users of the network as well. So we had to request to all the users and the TOs to get us any equipment that monitors any data on the network. Give us the data is what we requested. So this is where the problems start, because everybody has data in different formats. Everybody has to extract data, so it is not a straightforward thing firing an email saying we need data. It takes days for the data to arrive. So obviously the data comes in different forms and shapes. and then ESO has to sort of make sense of the data and understand if it's right or wrong and if it makes any sense. So data gathering is obviously something that happens after an event that happens in the network. But there are limited things we can do with the data. So in order to understand what exactly happened, we also looked at different parameters of the network, tried to understand what the short circuit level was on the network. We couldn't say that the instability was caused because of short circuit levels or inertia, because inertia levels were high on the network at that time. There was no issue with that. Short circuit levels were high as well, so there was something that we weren't seeing. But this is where the challenge comes for ESO, the limitations of user models, the limitation of the data we have, the quality of the data we have. And at the moment, this was obviously at the time when this thing happened, but even now we are still investigating the cause of the event as such. There are a few things narrowed down, obviously, with some controllers of certain plants perhaps causing interactions with each other. But in order to be very concrete about what was the cause of oscillations, we need detailed electromagnetic transient models of those areas of the network. At the moment, our modeling is based on RMS models. Sorry if I've lost a lot of people in this room. So RMS model is a average way of modeling parameters in the network, and EMC modeling is more detailed way of modeling electrical quantities. And it's the electromagnetic modeling, transient modeling, which becomes very important for converters because they behave very, very differently from synchronous generators. And going forward, we have a challenge of getting all the specific EMT user-based models and the models of the network as well built to be able to do more analysis. So there is a gap there, but it just shows that we have to, we need more insights on the models and the users and work with the users. But there are challenges getting the models because there are IPs from manufacturers. We don't have access to those models. But yeah, this ongoing work is just to give you a flavor of something happened. We're 2 years down the line. We can't exactly say what caused it because we can't concretely have a model of the network that says, okay, this is an issue. But yeah, that's where it is. But we are not seeing those oscillations anymore. Some users were asked to retune their network, retune their design. So as a consequence, because users had submitted data to us, we could tell some users that these tunings are not working for your control system, so they have to do something different. But yeah, that's what happened 2 years ago. But this is where we want to avoid getting there in the future. We want to have more access to models and network analysis.
Thank you, Janusz, Bialek. Interestingly, I've heard from Julian that on the exact anniversary of the first event, there were another similar event with oscillations, again, network oscillations in Scotland, and apparently some lights went off in Glasgow as well. So can you shed some light on that one?
I don't know about lights went off in Glasgow or not, but there were oscillations that were different nature of oscillations. So we know that this was a particular 8 Hertz oscillation. That was a different Hertz oscillation. And the question again goes back to having the models to understand the cause of the oscillation. The oscillations have disappeared, but and this is where the next step is getting user data to understand what the next steps are. But yeah, that's all I know.
Do you keep those?
Oh, sorry.
So do you keep those hydro plugs connected to prevent emergence of oscillations again?
No, not anymore. So that was only an interim measure when control room did not know what to do and what was the cause. Once we got the user data and we asked certain users to change the settings, the oscillations disappeared as well in the next few months. But we still don't know the exact cause of that particular oscillation. The issue hasn't, its issue is not persistent because the users have changed certain settings. But we can't really say what caused that issue at the time when it happened. But yeah, it's not a concern at the moment for the control room.
Just a quick comment that well, that issue is fascinating for me as an electrical engineer, and so I've been in correspondence with network operators in different parts of the world, and recently I got information from Australia that they also experiencing something similar. But in Australia, they do have exact models of the inverters because their grid codes request users to provide models, which unfortunately in this country is not happening. So they were able to analyze them, but I still think they have problems of duplicating them. But despite having exact EMT mod, EMT means, well, the difference between RMS is basically assuming that everything is sine wave. EMT means that it can be choppy, all of it, basically not idle sine wave. So despite having those more detailed models, they still couldn't reproduce those populations. So, that's why I'm saying it's interesting. It's a big problem and an area for all of us, for all the scientific community to research.
Yeah, so there's a lot of work that BSO are currently looking at regarding obtaining more accurate or more detailed user models, because without them, it's a point which was being made earlier in the session. If you have a model, you don't have the inputs, you don't really know if you trust the outputs or not. So having a model, but obviously having the right inputs is important. So having the right data from the users and right assumptions are important for us to know what's happening in the future. So we're looking at it, but the ideal place would be that we get more information from the users and the manufacturers to be able to do more with that. Yeah, so I guess I've said all of these things, but yeah, and just a last slide really from me. Just different things are happening if you haven't heard of them. So we have been running a few projects called Stability Pathfinders, where we have been procuring long-term contracts through a tender process. And we are procuring inertia and short circuit level as parameters in those contracts. And these contracts are up to 10 years in length. So this is probably the first time we have secured long-term contracts for these sort of services. And this is where the grid forming converter, there are 4 or 5 of them in phase 2 tender they were, and their battery solutions, and they're being built in Scotland. So we will be seeing more of these technologies perhaps as we go on and we develop more market mechanisms for people to participate. At the moment, the absence of mechanism obviously means there's an investment in technology. So they go hand in hand. Yeah, the grid code where it changes, the GC0137, which was the grid forming converter technology specification that's introduced. We are currently running an innovation project which should be finishing soon to define a market for stability. So market in the context, it could be a day ahead or a year ahead market, and a long-term market at least 4 to 5 years ahead, which is in line with the long-term tenders we are running at the moment. And the inertia monitoring I mentioned earlier regarding GE and the reactor technologies. This is probably finished now. So the accelerated loss domain program, which was running for past 2 to 3 years, was to incentivize the users on the distribution network to change their relay settings from 0.12 hertz per second to 1 hertz per second. So the distribution network generators were initially having vector shift, which was a different form of protection and a different relay setting, which meant that they could trip if the rock-off was really high. So this program's almost nearing its end now, and going forward, we'll be looking to operate to 1 hertz per second rock-off limit on the network. The rock-off limit only applies to the distribution network generators, not the transmission network generators. Yeah.
Yeah, and question about this last point. So, reducing of that number to 1 hertz per second, does it also maybe the reason why the cost of inertia, maintaining minimum level of inertia, went down in the last year? That was one of my previous questions.
So I believe this limit is not fully implemented. So 1 hertz per second is probably going to be introduced for next review. So because the program was still running last year, so it probably concluded last year. So probably from this year, we'll be looking at operating 1 hertz per second. Yeah, and if the rock-off we can operate to a bigger limit, means we don't have to constrain generation or add more inertia on the network, so we can relax our limits more. Is the idea of it. Yeah, I think that was it in terms of the slides I had. So probably stop.
You agree with me that the fascinating presentation. Thank you very much, Shurooque. A number of questions open to challenges for the scientific community for us to tackle. One thing which should be emphasized is that those problems are particularly important in an island system as GB. Of course, in Europe it's different because Europe is all AC interconnected, so basically they can share certain services. Ireland is even more ahead of us because it's even smaller than Britain. I mean, we've heard that the maximum amount of wind connected to the system was 66%, I think, of the. Yeah, in Ireland, they went 10 years ago, it was 50% non-synchronous generation. At the moment, I think they've increased to 75% due to a number of different measures. So basically, they are pushing back the boundary. We've had a number of questions during the presentation, but now we still have some time, 20 minutes, I think. So any questions from the audience, please?
Yes, so I'm very interested that the Australian grid codes require that you have a complete model of the inverter-based connectors. And the obvious point first is, if we know the manufacturer, can we borrow those? But second, I thought there was LCNF project to build a simulator to interact with inverters and actually characterize them in sufficient detail that you could model them. And I wondered what had happened to that.
I don't know about that project, so probably I will have to check. But there, on a separate note, there is a current project which Australians are doing as well, and which we want to sort of do as well, is having a core simulator environment where users can connect their models to a simulator environment where they wouldn't, because at the moment for us, the problem is users also tell us that they don't have the full GB model, because we can't share all the models, because we can't share all users' information with other users as well. So there's a bit of that users have issues with. So there is that idea of a core simulator where in an environment where a user knows where it wants to connect, it could connect, it could see immediate area perhaps with all the network parameters, but it wouldn't see the user wouldn't see everything else. So that's bit which Australians have been exploring and doing, so which we are currently looking at as well. In terms of the generic models of converters, we have models, we have generic models of converters. There's no issue with that. So there are different projects and innovation happened in the past as well. So we have a specific converter, generic assumptions, models, etc. But when it comes to event investigation, the generic models don't help us. Generics are great if you want to plan perhaps future investment issues, highlighting trends, insights, etc. But this is where the challenge becomes: if we don't have a specific user data, it becomes, and their control settings, it is very hard to say who has caused the issue or what issues are being caused by different users in the network or in the wider network. And that's where we want to get to. I actually don't know if Australians get the full models or not. They have mentioned they get models, but I don't know if they have to make assumptions or what the quality of models they get. Well, we do talk to AMO regularly to understand the modeling essentially, because they're quite far ahead of us in terms of modeling, where they are perhaps in terms of the EMT environment. And there's a lot to learn from them in that context, definitely.
Thanks. So, well, David and Shurooque between them asked and answered quite a fair bit of what I was going to ask. I was going to ask a two-part question. Well, probably now I said two-part, it'll be three, but about what is required here. The first is when we're looking to build a model of system dynamic performance, what are we looking for? So we obviously have the key high level parameter of inertia or equivalent inertia, and then are we also looking to estimate further more detailed parameters? If so, what kinds of things? I guess that you need to know much more in order to be able to understand matters like the oscillations in Scotland. And the second part is what the which you've already talked a bit about, is what is the state, approximately what is the state of the art in this, or is there any thinking of direction in which solutions like lie, because we, on the one hand, we've talked about possibility of being able to get models for everything, and my understanding is that there's a much wider range of possible dynamic performance from inverter-based resources as compared to traditional generators. On the other hand, there could be some kind of combination of measurement-based understanding of the system, which we've talked a bit about, at least in terms of inertia, with control, with a system control paradigm that's somewhat agnostic to, or maybe more agnostic to exactly what is connected to the system than the present circumstance. Hopefully that makes some sense, and it isn't too ignorant of power engineering.
Do you want to have a go?
So I think first part of the question regarding what else do we want to, so that I may have missed a few parts of the question. So of course, inertia is one element of it. Inertia is probably a relatively simpler thing to look at compared to the rest of the dynamics of the system we probably want to look at in more detail. So we do want to, in terms of understanding oscillations, as you say, we need much more than a normal dynamic characteristic we would normally study. So generally, we would, when we talk about dynamics in the context of traditional power systems, we are interested in rotor angle stability, how synchronous generators perform through system changes, will they become unstable or not? How does the voltage performance of the generator and others in the network is with regards to system changes, how they respond to frequency changes, and how they inject or absorb, etc. But with the converters and the oscillation concept, we probably have to consider regarding small signal stability, interaction of different converters with each other, how they operate at different modes, what are the oscillation modes, inherent modes within those converters or plants. So there's a lot more. We don't look at as system operators in general, even others around the world, because those things have been established for a traditional synchronous generator network. So these are things probably people are more worrying about, and hence we want to move to EMT environment, because these are the parameters we can look in that environment, which we can't look in what we currently do. So tools and capabilities aren't necessarily right for what we want to do in the future. Hopefully I've answered the question. But in terms of converters, there's a lot of scope. I mean, we talk about converters with a control algorithm, but they have a lot to contribute to as well to the network. They have a controlled matrix response. If you have the controller that works right in terms of providing response to the network for voltage, frequency, damping oscillations, there are so many things controllers can do. They can contribute a lot more than what we currently see them doing. So it's not all bad in the context that we have converters. It just means we need to have the right tuning of everything in order to know that we need different models and understand how users work with each other. Not sure I've answered all of the questions.
Just add first to that it's important to understand that there are those inverters, converters. Basically, the simplest way of looking at them. Okay, so we plot synchronous generators. So now we can program those inverters to behave like synchronous generators. This is a little bit like, you know, when the first cars appeared. First cars looked exactly like horse-driven carriages, because that's what we knew. So it's a little bit like that, you know. Why replicate synchronous generators? Think about it. They're pretty slow and sluggish devices. We can do better than that. But again, the huge area of future control application. What is the optimal way for those inverters to behave to give all the needs which system needs? Big area of research, very much uncharted. The second point I want to make, Chris mentioned measurement-based methods, and I think there are 2 points about it. The first point about it is that we will have those thousands or hundreds of thousands of inverter-based resources connected to the network. For EMC modeling, we can't model everyone, each of them, because the model would be too big. So how to do it is combine it. When you combine them, how to do it, and etc. and etc. So the other way is using this measurement-based method, and for example, the inertia measuring, what you was mentioning, reactive technologies and GE, are both measurement-based methods. you get what you see. So in terms of analyzing those new power system dynamics, again, this is approach which I'm trying to follow, and I'm doing that with Ingrid from Imperial College, is just to look, rather than coming from EMC modeling, it means we model something and we don't know how good the models are. We try to develop higher order models based on the measured response. So those are like not black box, it's like a gray box, combination of modeling and combination of system identification, which again is an old area of control. So again, these are new areas of research which are being opened for us and very exciting, completely new thing.
It's an important point about it's easy to forget about design of devices. Frank Kelly says this about comms networks where control architectures and devices would be designed in coordination.
Lars Schever. So, yes, sorry? Yeah, it just said my name. Yeah. Lars Schever, University, just said my name. So. Yeah. So I was wondering in terms of going off of what Chris said, state of the art. So the models that are currently in use, can they, assuming you sort of build an artificial network for a second, can you replicate similar effects, or are the models that are in use not able to show this effect? That was, for me, it's sort of, if we are talking about all the models that we're building and so on, if the models that are currently in use are sort of unable, even in the synthetic situation, to replicate this thing, then we need to think about completely different models. Whereas if you say, no, they can replicate it, then it's more of a data question. So for me, the question is, where do you think we sit there? I probably sort of a not clear-cut answer, but where do you think we sit? Do we need different models because we can't replicate this at the moment, even in synthetic situations, or not?
Have a go.
Yeah, sure. In the context of what we see on the system, when we try to because control room will have different models and tools that you online stuff it uses. We would have offline stuff we use. And it's a challenge becomes as well, even if we consider the same network model with the same information, sometimes we think it's the same information, we don't know. This is also a problem. We don't always get the same answers. When I say always, I think most of the times we would never get the same answer because we are using two different things, tools and processes. So there is an argument that we don't know the answer if the data is completely different, or the way the two tools are treating the data is different, completely different, because there's slight changes in between. So there's a combination of, yes, the data could be different, but there's also how the models work could be different as well. And I think it's the both questions are probably valid to ask. I don't know the answer because I don't know what the right answer is, because there's a balance between how much modeling you do and is our modeling going to give you the right answer, or versus the level of information you could have, like with information you could do with less modeling. There's always that point.
That's why I was wondering whether it would be worthwhile to think about sort of a small, non-real, but sort of synthetic example with the models that are in use to see whether one can replicate such a sort of event, to see whether the model in principle can do this. And the question is whether anybody has done something like this to sort of test out, can we actually build a small network that looks just similar, and some converters that sort of get these sort of 8 Hertz oscillation, or if
that's exactly what's being done
for
the Scottish oscillation. So the Scottish TO, the SSCN, they're building an EMC, a detailed model of the part of the area where they saw the oscillation. And the challenge when it comes to EMC is the hardware limitations. So they have hit a hardware limitation point that they need to invest in more hardware to be able to do more computations. Okay. So, but that's exactly what's happening. So they are trying to replicate the events with a smaller area of the network, and that will be the principle we would apply, because in order for us to run a simulation for a whole GB network in an EMP environment, at the moment with the capability, the tools, the hardware and the software capability that we have, it takes us like more than a day to do so. So we can't do it. So we'll have to look at some areas of the network, segregate them into one and more detailed network analysis, perhaps. But there's a limitation of computation versus the tools and hardware.
So the software that you would be using at the moment is sort of off the shelf. So you're not talking research software. This is sort of off the shelf software that you can use, and that is available. So just to see where on the technology we are with that. So that's off. Okay.
Yeah. So CAD software, where manufacturer of the software is heavily involved in actually building the GB network with us. And the same software is being used by Australians for their network as well. So we're trying to benchmark on those things. But it's a challenge modeling new things in new softwares and the computation time it takes to be able to do them. And when you talk about dynamics, you want to do more analysis, you want to run like faults on the network with time simulation for all the areas of the network, which is not possible with the models we've got.
It's just coming back to this issue of electronics manufacturer not disclosing their control policies. I mean, we're inevitably moving towards a power electronics grid. I mean, isn't this going to create kind of an incompatibility with your role as CSO? Or if we have a power electronics grid and the control policy of the power electronics determine the stability of the grid, and you as CSO are not aware of them, how is the grid going to operate? Then we need kind of new regulations so that these control policies are disclosed, and actually, even more importantly, ESO restrict the kind of control policies they implement so that the grid is going to operate.
So, I mean, anybody who connects to the grid at the moment, converter or not a converter, they have to obviously pass through a compliance stage before they connect. And as part of the compliance stage, to connect to the grid, they have to provide us lots of information, including lots of simulations against the grid code obligations. So we would expect to have some understanding of the behavior of the converters with regards to what we've asked them in the grid code. But the problem is that we don't know all the behavior of the converter because we don't know exactly how that control algorithm is working. So we may not see what we don't currently see an issue in the future if we don't have those models. But that's the idea. We want to get more data and we want to get more information from those manufacturers. But getting to a stage where industry can accept it and the regulator would then approve it is where we would have to go to get that change. But yeah, you're absolutely right. Without those, we can't see. We're probably blind without those. So.
Any more questions?
Just if there are no more questions, I just want to say something about next session.
Yeah, okay. Well, so thank you very much, Shurooque, once again for excellent presentation and dealing with all the questions from the audience. So once again, thank you very much.